Okay, so this is joint work with Mohammad, Akbarpour, and Amin Saberi. So thanks everyone for making it out to the last talk of the day. So let me start by describing the optimal seeding problem. So imagine a network with n individuals and fix some diffusion model which is going to describe how communication happens over this network. And suppose that we as policymakers have access to S seeds or individuals who we can initially inform to jumpstart this diffusion process. A natural question to ask in this setup is what is the optimal set of S seeds to give information to if we want to maximize the total number of people who hear about whatever it is that we have to say. And in a very influential paper, Kemp, Kleinberg, and Tardos showed that this problem is NP hard, even for sort of simple diffusion models that we might write down. And following this work, there's been a lot of interest in studying the optimal seeding problem, particularly from social scientists who've gone on to identify many situations where it naturally arises. And the applications include word-of-mouth marketing, spread of political ideas, and most recently in development economics, where starting with the work of Banerjee et al., 2013, people have started mapping out social networks in dozens of rural village networks and studied things like the spread of microfinance, uptake into weather insurance programs, spread of new agricultural technologies, and so on. And what have we learned from this empirical literature? Well, now we have a large body of evidence pointing to the fact that taking into account network theoretic considerations when making seeding decisions is actually very valuable for policymakers. And here are just quotes by Banerjee et al. And Kai et al. Saying pretty much the same thing. But given that these optimal seeding problems are difficult to solve in general, people resort to heuristics, which involve basically, in general, ranking all the nodes in a network according to some relevant measure of centrality, and picking the top S individuals as seeds. Now, while these methods are computationally feasible, they have the caveat that they all require network data to compute. And of course, network information is assumed as a primitive in the optimal seeding problem. But in a lot of settings of interest, it turns out that it's actually quite difficult to obtain network data. So for example, with survey methods, there's the usual concerns about misreporting, particularly if the answers to those survey questions are going to determine who receives, say, the allocation of a new technology. Also, we might acquire some sort of network information, but it might not be the relevant network of relationships to study the information process we're interested in. There's a more basic problem, which is it might simply be too expensive to be a policy-relevant recommendation. And so in the literature, there's some proposals to address some of these concerns, either reducing the cost of acquiring network data or circumventing collecting any network data at all and directly coming up with other simpler methods to identify central seeds and so on. But even if acquiring network data were costless, it still makes sense to step back and ask, what happens if a policymaker were to entirely ignore network information in making these seeding decisions? How much worse off can the policymaker be? And to give a flavor of the analysis that we're interested in, consider the following example from the Diffusion of Microfinance paper by Banerjee et al. Here we can take their network data, and we can take their model of diffusion and their structurally estimated parameters, and simulate various seeding strategies and compare their performance. So I do just that in this graph here. The x-axis is the number of seeds used by the seeding strategy, and the y-axis is the total amount of diffusion achieved. Here, the green line is the performance of the random seeding strategy, and the blue line is the performance of a seeding strategy which picks diffusion central individuals, which is the prescription of the paper. So here we see that in line with their findings, diffusion central seeding performs significantly better than random seeding everywhere. But it's interesting to note that a random seeding strategy with 4 seeds already starts to outperform a network-guided heuristic with 1 seed. So this observation leads us to ask more generally, in a variety of applied settings, what is the value of actually collecting network data? And we want to pose this question in the following way. So on the one hand, consider collecting network information and using that information optimally to seed S agents. On the other hand, we can ignore network information entirely and seed S plus X agents randomly. And so the question we would like to ask is, for what values of X does random seeding beat optimal seeding? And the answer to this question is going to quantify the value of having network data and using it in an optimal way. And just as an aside, the question we're asking here is analogous to the result of Buehler and Klemperer in auctions versus negotiations, where they show that an optimal auction with n bidders yields less expected revenue than a simple auction with n+1 bidders that requires no information to run. Going back to our setting, going back to our setting, we basically we don't have enough structure to say something as tight as the theoretical results of Bulow and Klemperer. But what we believe that the analysis is all the more relevant for the optimal seeding problem. In particular, because a auctioneer might not be able to fine-tune the number of bidders who show up to an auction, whereas a policymaker can definitely divert resources that they would have used towards implementing a more sophisticated seeding strategy to simply expanding initial outreach. And just to give you a preview of what's to come, we basically, through simulations and theoretical results, are able to show that for a certain class of diffusion models, either the number of additional seeds required is small relative to the size of diffusion it produces, or that the total amount of achievable diffusion itself is small. So this suggests to us that perhaps the right policy recommendation when we find that random seeding is hopelessly bad is not to upgrade to a more sophisticated seeding strategy, but to avoid word-of-mouth communication as a useful vehicle of information transmission altogether. Okay, so with that, let me go to our model. N is the set of agents, and G is a network over these agents. And here is our simple diffusion model. There is a node who is going to be initially informed. He's going to communicate with probability C with each of his neighbors. One of these communications here is successful. Now the initial node is going to be dormant. The new node is going to communicate with probability C with each of his neighbors. And this process is going to continue until there are no newly informed nodes. Okay? And a network model is just a probability distribution over possible graphs on n nodes. And for simplicity, I'm going to state results for Erdős-Rényi random graphs with constant expected degree as n grows large. And I'll mention the extensions that we have in the paper for other models of graphs. A seeding strategy is a mapping from a graph and a budget of size S to a set of S seeds. So for example, degree GS returns the S seeds with highest degree. Ran GS returns S seeds uniformly at random in graph G. And skipping over some of these formalities, opt is an optimal seeding strategy, which just picks the set of seeds which are going to maximize expected diffusion. The omniscient seeding strategy is one which actually observes the outcome of a diffusion process prior to making seeding decisions. So it uses this information in a cheating way. It's obviously unimplementable, but it's going to be a useful benchmark in our results. So one last piece of notation, capital H is the expected diffusion where the expectation is being taken over the randomness and the realization of the graph, the outcome of the diffusion process, and any randomness in the seeding strategy. So now I'm ready to state our main theorem, and then I'll go on to show you proof ideas which you'll see will follow pretty straightforwardly from results in random graph theory once we adopt the correct perspective. So here, we say let S be little o of n over log n, so sufficiently small, and DC being greater than 1, which means that in expectation, each informed node is going to communicate with at least one of its neighbors. And let xn be a superconstant, so imagine any slow-growing function that doesn't asymptote. Then the expected diffusion of a random seeding strategy with S plus X seeds is going to be comparable to that of an omniscient seeding strategy with S seeds. And when DC is less than 1, even the omniscient seeding strategy is going to produce a diffusion which only reaches a vanishing fraction of the total population. So here's a proof idea. Here we have a social network. Now we can step back and use the usual trick of thinking ex ante who would speak to whom before we make any sort of seeding decisions. And so I've highlighted these edges in green. And so this subnetwork, which we call the communication network, is actually the information that the omniscient seeding algorithm is privy to prior to making a seeding decision. So what is an omniscient algorithm going to do? If it only has one seed, it's going to put one in the largest component and get all of those nodes. If it has two seeds, it's going to put one in the largest component, one in the second largest, and so on. A random seeding strategy is going to seed these components with a probability proportional to their size, and it's going to do so redundantly sometimes. So now as some of you might have guessed, if we have this DC greater than 1 condition, that we're going to have a giant component in the communication network, and it's going to suffice for the random seeding strategy to place at least one seed in the giant component in order to have a diffusion which is going to be comparable in size to that of the omniscient seeding strategy. And whatever the omniscient does with the remaining components is not really going to matter in the asymptotic sense. And when DC is less than 1, all the nodes are all the components of the communication network are going to be small. So all seeding strategies are going to perform fairly poorly in this world. So things are a little bit more interesting if we looked at directed communication. So you'll notice that in the previous slides, I said that as long as you seed one node in this component, all the nodes in that component are going to be informed. So essentially what this communication model assumes is that the event that A speaks to B is coupled with the event that B speaks to A. But it might actually turn out in reality that if I give Alice information, she might communicate that with Bob, but were I to give Bob information and not Alice, Bob might not have done the same thing. So we instead move to a model of directed communication, which seems more natural. So this is what communication graph for a directed communication model might look like. So in the dotted circle, we have a strongly connected giant component. And if you seed any node in the strongly connected giant component, all the other nodes in that component are going to get information. However, you now have paths that are leading into the strongly connected giant component, which aren't themselves part of it. And so if these paths are particularly long, omniscient seeding algorithm might actually pick a node at the edge of one of these paths and collect all of these yellow nodes as well, in addition to everything in the strongly connected giant component. And of course, if these paths are not linear in size, then it could be an issue for random seeding to quickly catch up. So we're able to show that, in fact, these paths are order log n in length, where the best bound we were able to find in the literature was that their size root n. Okay. So as I mentioned before, we can extend our results to other other network models. For example, models with power law degree distributions and models with clustering, and by the way of simulations, using actual network data as well. And I mentioned a couple extensions with changing the diffusion model. So we can think about directed communication, and we can simulate some of the models that are used in the applied literature. But it's not true that in general there aren't sort of diffusion models for which seeding does matter. For example, if we think about a threshold type diffusion model where agents will only adopt a technology if a certain fraction of their neighbors adopt the same technology, then we can't hope for a random seeding strategy with a few seeds to hit the neighbors of many of these individuals unless they're very central individuals in the network. For similar reasons, if we were interested in stopping a diffusion process from happening rather than creating one, then we would actually need to know something about the network structure so we can sequester something like an infection into a small component and strategically break the links around it. And just randomly breaking a small number of nodes or links in this network wouldn't actually get the job done. So just to sort of give an overview of what I've said so far, we have here the random seeding strategy. We can move from random to a heuristic seeding strategy with imperfect network information. And if we followed the prescriptions of some of the applied network seeding literature, this is the benefit that we would get. Alternatively, if in an ideal world, if we had perfect network data, we could conceivably do better than that. If we had the computational resources, we would be able to do optimal, which is better. And if we had access to an oracle, we could reach the omniscient. And for some diffusion models, it might be the case that this gap itself is easily bridgeable if we open up to the fact that the policymaker doesn't just have a choice over what sort of seeding strategy to use, but also has the other policy arm, which is determining how many seeds to use. Now, as a takeaway for applied work, we don't know in different contexts whether it's actually going to be the case that using a random seeding strategy is going to be sufficient. It might be the case that random seeding would do fairly poorly, and it's simply that the models that are being used to describe the communication process are producing the incorrect comparative static. So as a suggestion we have for future applied literature is to essentially report the number of additional seeds required for a random seeding strategy to catch up to whatever network theoretic heuristic that they propose. And this we see as a useful and easily interpretable statistic for policymakers to have. And so here, it's just a table to show that, at least for the model of diffusion assumed in the microfinance and weather insurance papers, the number of extra seeds that we seem to need seems fairly small. Thank you. Sorry?
Do you know some harness result on your model if your graph is further training graph?
Mm-hmm.
Consider genetic escape. Do you know some harness result of that?
Sorry, I don't think I fully understood your question.
Do you have any hardnesses or something on your model?
No, I don't. Sorry. Oh, on the diffusion model that we assumed? Sorry? I believe it's NP hard.
No, I mean the further training graph.
I don't think so, but I also don't know that I fully understand your question, so we could maybe talk to you offline.
Thanks.